Hopefully you do now, because I think it's fair to say that those homeworks are on the test. Obviously questions just like that. And I'll be late, I haven't started on it yet, so, and I'll try to make it a little easier. We are going to have still some 14 grams of nitrogen. How many moles? How many moles? 1 mole? Half. Remember, N comes in N2, 28, not 14. All right, so half a mole of nitrogen expands at 298. What? Delta. W, Q, all that stuff. But now you've got entropy. Entropy inside, entropy outside, entropy total. So, and I know last Monday, I don't know, I just was not, I guess I wasn't prepared enough. I know it's just a lot of crazy stuff, and a lot of it didn't make maybe a lot of sense. I kind of felt like I was being a little incoherent that day. So we'll review. Let's see, again, your test come back Friday. I've got your present homeworks. The next test is a ways away, it's not even worry about it. We are actually wrapping up this whole gas expands and gas contracts. We're getting really close to the end of it. And anyway, I guess that's all class business. Anybody probably don't have questions? I won't be skipping, I skipped out office hours this week. I won't do it again because you had your homework, so I know you want office hours. Sorry, I just had to read things come up. Nothing cat-related, but anyway, that's a shame. Okay, remind you what we did last time. We started with, again, so that my notation isn't bad, something nuts, N, R, L, N. And remember, we did this by figuring out what heat. Okay, we start out with this, albeit narrow definition of entropy, the chemist definition, and I was able to relate heat to work, which gave me this thing. And when I was talking about heat exchanges, it reminds you not to make that mistake again. Heat capacities are not per mole, natural log PI. And now, again, for system entropy, because there's no subscript, this always works. So you always got that. So this part is actually relatively easy. But I threw at you the hard part, and I'm not going to write it down. It's when you do the total and how that's the change of the surroundings plus that of the system, where this is actually easy, but these ended up being easy but case dependent, and I don't have a good out for that. All right, now I wrote down a chart last time on how to do the 4 conditions for this, which obviously gives you that. Let me do it again, but not write it down. You already wrote it down. I'm not going to write it down again. Let me just tell you what's going on in my head. I knew, am I the test? I just got isothermal reversible. Okay, reversible, that's 0. All right, because that's the definition of reversible, another thing I wrote down last time. If that's true, then the surrounding resistance minus that of the system, and the system was easy to calculate. Okay, I got that one. Isothermal irreversible. That's the one that's a real pain. That's what I remember. I remember that's the one that I can't define, and I know that irreversible things, I know all things either have to have this 0 or greater than 0. I remember that isothermal irreversible is the sticky one, the one that's undefined. So I therefore conclude that this is greater than 0. And I know not to go less than 0 because I know that's impossible. That never happens. So I know that this is greater than 0, and then just do the math. If this is now a greater than sign, this has to be a greater than or equal to, if I'm isothermal irreversible, it's greater than minus that. Okay, again, that's kind of difficult to remember, but then how can you think of that? Okay, if this is negative, if this is minus 1, this has to be greater than 1, right? To wipe out the negative and add a little bit more. Okay, again, if you get confused, that's how to remember it. If this is minus 1, that has to be greater than 1, greater than minus the system. All right, if this is 1, this can be less than, this can actually almost be negative 1. See, you can gain inside and lose outside, that's fine. In fact, that's probably what is going to happen, in fact. But if this is minus 1, this can't, if this is plus 1, sorry, this can't be less than minus 1. It can't be minus 1 either, because then you wipe it out, and then the total is less than 0. So again, logic, just let it flow. All right, because I can't do better than that. Adiabatic reversible, everything's 0. Adiabatic reversible, automatically this is 0. There's no heat transaction, so that's 0, everything's 0. Adiabatic irreversible, again, this is greater than 0, but that's 0, therefore the total is that. Okay, again, no notes, did it all, it's not impossible. But that's what you're going to have to do, and that's why entropy gets to be something easy, unfortunately, turns into something a little bit painful. Okay, then I started talking about how a change, we talked about what makes things spontaneous. If total entropy change is greater than 0, equilibrium, total entropy change is 0, total entropy change less than 0 never happens, never occurs. Okay, now remember I also said that this is the symbol of note, is exact. Therefore, S has a functional form. But that was really difficult. So it's easy to see that I've got these partials and whatnot, and it seems like, well, I should be able to just do an integral or something and get the functional form. And it just doesn't turn out to be that way. It turns out that because entropy is a randomness, and randomness must be a probability, and probability is multiplied, but entropy is also a state variable, it must add. It was a function, the functional form, not the change in S, and S itself must be equal to the sum and the multiple of, say, two coupled systems like this. And only natural logs do that. So what we found was S is ln, this thing, I call it degree of randomness, or a number of microstates, which again is a graduate level concept. I'm going to introduce that because it's kind of neat and it's how things work. Now, I don't have units, so what I'm going to do is introduce the gas constant, but what I like to do is think about individual molecules because I haven't really done much of that. And so I take the gas constant and divide it by Avogadro's number, and that gives me Boltzmann's constant. It's the same thing. It's the exact same thing for a molecule, whereas R is for a mole. So now I introduce this model system here, and again, you don't have to rewrite it. So don't rewrite it. You already have it written. You got videos. If you get confused, I think I kind of got myself a little bit confused about this. I have to reread it, make sure I understood it. Now again, graduate. So this degree of randomness, I'm telling you that there's only half a way to pack half the molecules on the left side, and there's only half a probability of finding molecules on the right side, so that's where the half comes from. And I know that because I went to grad school. If you don't know that, you just have to trust me here. And I know that I have to consider that there's n half on this side and n half on that side, and so I raise it to that power. That's the multiplicative property of probability, half, 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 half. There's a half a probability that the first molecule is on this side, half a probability that the second molecule is on that side, and half a probability on and on and on for n over 2. Because I put n over 2 molecules in that side. All right, so that's the multiplicative aspect of probability kicking in. Again, graduate level stuff. There's only one way, once I remove the partition, this is a partition, I remove it and I let the gases mix, there's only one way for that final state to exist in that mixed form. I hope that kind of makes sense. I can't actually do better because entropy is so hard to understand. Okay, entropy of the final minus entropy of initial is this. And what I ended up with was NKD, natural log of 2. And that's no different. I didn't say there was a heat transaction. In fact, it's adiabating. And so it looks like for any particular side, the volume doubled. And I have n molecules doubling their volume. So they end up being the same thing. Okay, again, I hope that's not too painful. And as I told you, I'm going to do it right now. Let me show. I will have this on the test. I'll have it on the homework. I have ways of making this whole microscope thing. I have ways of making it really easy. This is what you'll get on your homework and test. Okay, so another way this tends to be expressed. When I use the microstate term, degree of randomness is I use that for rho. When I talk about microstates, which is the same thing. People tend to use the symbol W. Again, this is our human stupidity, giving things multiple names. But this rho and this W are the same thing. Number of microstates. Okay, now what I gave you here was a probability type of picture. And that's fine. It's a little harder to understand, and I don't know why I start with that than this number of microstates picture. Again, this is actually the same equation. All right, real easy. I got 3 holes, and I got 1 piece. How many ways, how many states do I have? How many ways can I arrange that piece? Now, all the holes are the same, and this thing can hop with no energy. How many ways can it hop? How many spots does it have? 3. Yeah. Right, so there's the W is equal. Okay, so a slightly harder one. Okay, if this is the case, then S is KD ln 3. Now I've got the total entropy. And then I can start thinking about entropy changes and all that other stuff. Okay, let's do a harder one. 2 players, 3 spots. How can I rearrange? How many ways to rearrange them? Now, the X's are identical, so you can't put a label on it, that doesn't make sense. And the holes are all equal. 3, right, there's 3. I know, permutations, right? Remember that entropy is probability, and probability can be thought of in terms of permutations. Something I'm particularly bad at, but, well, I guess I need to be good at it. So I still have 3 microstates. And so I'm going to say that this is the entropy, and if this is a 3-point question, I just got 2 points. I did something wrong. This is not correct. This is correct. This is not correct. There's a hint. You know I leave hints. What's missing? What's that?
The extras.
Nope. That number of spots, no, it didn't matter here. Well, it did, but what was ultimately different? What's one thing different between here and here?
The number of X's.
Number of X's. So therefore, when you think I'm missing 2, I'm missing a 2. Right. Remember, entropy as a state variable is extensive. I told you yesterday that I got a cat in my house now, but then I got a second cat. Things are twice as nuts now. I'm sitting in my chair. My one cat's like really affectionate, so she tried to jump up, but she tried to jump up through the chair. It's stupid. She had to go to the hospital, actually. No, I'm just kidding. Okay, so entropy does need to be extensive, so you have to count the number of players. That'll be in your homework, by the way. This next homework. Okay, now let's do this one. Is this one pretty interesting? zero?
Oh, 1.
Right, it doesn't. Now, when you say that there's no microstates, that means it doesn't exist. That's the entropy of a vacuum. And I need to be putting units joules per K. Okay, so guess what? You just proved the third law of thermodynamics. I'm not going to bring it up again for another 2 more days. But the third law of thermodynamics, don't write this down. The third law of thermodynamics says a perfect crystal at 0 degrees K. That's the temperature part up there. So you need to be at 0 degrees K. But if you have a perfect crystal, the entropy is formally 0. That's actually the third law of thermodynamics. Largely just proves the second law. The third law just says entropy exists. And entropy is, that entropy tells you how everything works is the second law. And the third law says, yes, by the way, entropy is real because it can be measured. That allows us to measure it. So now, again, these are the type of questions you'll get on your homework, and I always have them on a test. So, not hard. Let me raise the notch a little bit, because I do want to push you a little bit mathematical stuff. Because you're heading to 346 now. I don't think you're going to be doing this in what I'm about to show you. You're not going to be doing this in 346. If you go to 444, that's PChem 3. We used to require 444, by the way, but through the college forced us not to. Now this, if you do take 444, which is what you want to do if you want to go to grad school, that's a really good idea if you want to go to grad school in PChem. PChem especially, or really any chemistry, but especially PChem. There's usually at least 1 or 2 of you that do that. Let me show you a whole other way to do this. Okay, I got the magic box with the magic partition, and I'm going to work the same problem I did, just with some slight differences, just because it makes it understanding a little bit easier. So I'm going to work that other problem, the one that I use the degree of randomness, that there's a probability of only half being on the left side and a half being on the right side. And then there was only one way to have them mixed together. That one I think is hard to see. And this one might be slightly easier. What I'm going to do is I'm going to talk about microstates. Instead of probabilities, I'm going to do microstates instead. And I'm going to do permutations. Okay, so let's see. Initially, so the initial number of microstates. Unfortunately, I have to kind of bring up a probability type of statement again. How many ways can you stack n molecules on the left side? How many ways can you permute the positions of molecules on the left side and to the left side? Well, that's a null statement. Well, they're already on the left side before, of course, we release the partition. Right, so you need to write that down. We release the partition and we mix the gases. That's what this is all about, calculating the entropy. There's only one way to put those n molecules on the left side if that's all that we're seeking to do. Okay, now after we're going to release the partition and the molecules start moving here. So I'm sorry to draw over my own figures there. I try not to do that. And I hope your notes, you can follow your notes. If not, that's why we have videos. Okay, now what I have to do is figure out how many ways can I partition n molecules on the right and n molecules on the left. And I'll be real friendly, the volumes will be the same. Obviously, the left side and the right side volumes are equal. Now, who remembers their permutations? 6 cups, 3 ping pong balls. I don't remember this at all. I had to go to Wikipedia. Okay, so it ends up being, in fact, yeah, remember factorials? When you're doing 3 balls and 9 cups and all that. How many ways can you, and then it matters if they're like, each one's a different color. At one point I understood that stuff, but I had to look this stuff up. But I do remember there's lots of factorials involved. Okay, and this is number of ways to place left or right. And again, this was 1 because there's only one way to place all the molecules on the left, given that there's only one left side. Okay, I hope that makes sense. Now again, I just Wikipedia this. This is 1,000 cups, and 500 ping pong balls. They're all the same color, and so I Wikipedia, there we go. Okay, so now, the initial delta S, of course, is going to be S final minus S initial, and so the S initial is 0, because when I have natural log of 1, I hope that's obvious, I'm not going to write it down. And so that means that S final is actually the change in S, and that is KLN of that monster there, n factorial, I'm just going to write it over again, n over 2 factorial, oh God, this is awful, isn't it? Okay, and then it gets a little bit better because I have a lot of, I'm going to do a lot of identities of natural logs. I've got natural log of n factorial. Okay, then I'm going to subtract the bottom. KLN, ln, n over 2, factorial. Oh God. Squares, oh, I'm moving an awful job. I know that looks awful, doesn't it? But it is what it is. I guess I messed up my brackets or whatever. Anyway, okay. Now, here's a trick. Now, this is a graduate level thing, but I think you can hack it. And it's good for me to push you sometimes in harder math because that's where you're heading in a big freaking way, especially if you take full four. That's called Stirling's. Stirling's approximation. Any of you hear this? No one? Oh, come on, no one? Come on, I heard this in high school. When we were doing, 5 cups and 3 ping pong balls. That's this. I'm kind of surprised. I knew I saw this when I was your age, but I didn't have any use for it. It turns out when X is very large, you can make this approximation. When X is like a mole, this approximation is accurate to like 1/1,000,000,000 of 1/1,000,000,000 of 1/1,000,000,000 of 1%, meaning that the error of this, well, sorry, I should, don't change your notes, don't change your notes. I just want to be as accurate as possible, but don't change your notes. When X gets large, this just isn't an approximation. And to what degree it is an approximation could never, ever be measured. We make fine measurements, but we can't measure errors to 1/1000,000,000 of 1/1000,000,000 of 1/1000,000,000 of a percent. No machine can do that, and why should you care? So now, here's another big picture thing. And again, it's not going to be part of this class, really. This is just how it is. I just wanted to let you know how it is. When it comes to really deriving all the thermodynamic stuff that like we did, or the more advanced things that you're not going to be exposed to, we do it with KLNW. That's the beginning. Guys. Yes. So we do it with KLNW. And that gives us entropy, and then that gives us everything else. We're clever at that. Every derivation involves Stirling's approximation. So this is an important lesson that's, again, a graduate level, but that's okay. That is that thermo only works because you have large number of molecules. You can actually violate thermodynamic principles on very small scales. I can violate the conservation of energy. It's actually really easy to do. We've done it before. But you can't see it happen when you have very large numbers. And again, in the big picture, that's because deriving any thermodynamic relation properly involves this stuff, it involves this, and it only works when you have large number of molecules. So, again, not part of the class, I just want you to know this is how everything works. And maybe you're not interested, but, well, it's spooky would be, but anyway, all right, I'm just rambling. Okay, let's use this. And I always get a little cross-eyed. Okay, so I got that. So that's Kn, ln, minus Kn. That guy's always there, right? So this. Okay, then I got the second term, which is a bit more complicated. Okay, I can bring down the 2. So I got 2K. I brought down the 2 out of the natural log. Then I've got n over 2. Is that right? Yeah. That's this, and over 2. There. And then I'm going to subtract, but I've already subtracted, so I'm going to add, again, 2k and over 2. No, wait. I forgot the natural log. ln n over 2 minus plus 2k n over 2. I know I've done a couple of steps of algebra, but it's whatever. Okay. So again, if you go to grad school, this is what you're going to see. So those clearly cancel. What I've got left is k n natural log of n minus kn, so I can see I can factor natural log. So I just have to deal with the natural logs. Natural log of n over 2. Okay. Now I'm going to factor kn natural log of n over 2. Okay, I know that's a little awful. Obviously now I'm almost done. That's kn natural log of 2. What's wrong with me? Handwriting's bad today. Okay. Notice it's the exact same answer I got before. And notice if I say delta S, this is delta S, is NR ln the F over VI. What I do is I take N and make that number of molecules divided by Avogadro's number, but then R divided by Avogadro's number is K. That ends up being NKB ln 2. The exact same answer. There you go. So, one last bit. And again, I hope I hope you don't think I'm wasting your time on graduate level stuff. Knights of the chessboard, yes. I do want you to know that S does have a functional form. This is it. I can't simplify this. Remember, those equations I gave you before are for changes in S, not S itself. There is no simpler form. Expect these types of questions, but understand this is what grad school is about. You think, well, screw that. Well, guess what? You get paid to take classes. How do you like them apples? I'm surprised how many people don't know that. Every now and then I talk to someone like you get paid? No, you don't get paid a lot. You get paid about $25,000 a year. But you're getting paid to go to college. And the reason is that as chemists, you might discover something. So one of our graduate students, 9 years ago, discovered a drug. We have made $100 million off that drug. So the potential of you making a discovery worth, I don't know, a freaking $100 million is so high that it's worth paying all of you to go to grad school. Northwestern, are you heard of Lyrica? One of the grad students came up with, under the professor got all the credit. I mean, let's not kid ourselves. I'm sure 1 or 2 grad students, 2 or 3 grad students worked on it. $1.6 billion is what they got for Lyrica. These couple of people in the lab generated $1.6 billion. Now, the guy who discovered it, the PI who gets to negotiate, take us how much he got? $800 million. $800 million was his. He told one of my friends who's a professor at Northwestern, he said, they're in my bank account. I'm sure the guy had plenty of money, all right? Now, I had plenty of money. And I grew up in the housing project like a lot of you did. And he says, I look at my bank account, and I'm sure there's a lot of money in there. He said, then I looked at it again, and it was actually, at the time, they sold only half of it. He said, then all of a sudden I saw $400 million in his savings account. So, and he still brings a brown bag to lunch every day. If I had that kind of money, I'd have Emerald follow me cooking. Because I could. And it would be worth it. Okay, last bit. Does grad school sound like a good option now? Does it? Huh? You get paid, you might get rich. Now, you probably aren't. That's like getting hit by lightning. But some people get hit by lightning. It's going to happen with someone. It might be you. I don't know that. Okay, before we go all nutso on each other about how rich we're going to be in a couple of years. 25 is not bad either, all right? You don't need the big bucks. All right, now notice I'm always relating volume to microstates. It just kind of, it just happens to give me the same answer, sure, but there's more to it. Why is microstates kind of proportional with volume? So it begs the question, again, the hard part you go to grad school to make that $1.6 billion, those were actually organic chemists, but anyway. Why was it that, so what does it come down to microstates? When you go to grad school in PChem, you take StatMech, which is what I'm talking about, and you learn how to count microstates. And I'm telling you, in this case, it's basically, the number of microstates of a gas is basically its volume. But what is a microstate? It's the number of ways you can create the thing such that I have another copy, it's different, but I can't really tell. All right, so that's kind of what that means. So if I think about gas in a box, let's put a gas molecule in. I guess another so that's one microstate, and maybe don't even write this down, but I bet I could have put it here. And I bet that's like another microstate, because again, if I have this little box with this gas molecule in it, you know, do I really care where it is? You know, really? Do I? I mean, it all seems the same to me. So all of these, it looks like I have 1, 2, 3, 4, 5 microstates. 6. Again, I should be drawing individual circles, but it looks like these look like different states that the gas could be in the little box, where it could be. And I just don't see it as being any different. Besides, the damn thing's whizzing around like a bee anyway. So, and therefore, maybe like this. I'm being very whimsical, by the way, because maybe this is not a microstate because they're kind of the same. They're kind of not the same. So I don't quite see this as 2 microstates, but I see like this as 6 microstates. But anyway, I just wanted to throw that at you. I know this is a big side show, but and anyway, so let's forget about this for now. Just remember those kings on a chessboard. You'll see that again, because it is important. I want you to know what this stuff is. All right, now, remember last time I talked about the Clausius inequality and how I was going to bring it up, forget about it, and which is what I just did, because I wanted to show you all aspects of entropy. Now let's go back to it. Because I told you it was the most important thing ever. Clausius inequality, let's go back. Okay, and recall that is, I expressed in 2 ways. Okay, hey, come on, I know, we're after a test. Notice that I'm also talking to you like I talk to my cat. No, kitty, no. Okay, now recall, we're going to work with this one here. Don't worry about this one, these are the same thing, right? Now recall that, in case you forgot, where this came from was our knowledge that reversible work is always the greatest negative, the greatest magnitude, but always with a minus sign, even when it's positive. And I proved that with graphs. We then said heat and work can do the opposite things in isothermal reversible. We made it isothermal reversible. We started thinking isothermal reversibly, which is fine. We can think about it any way we want to because of path independence. And so we said if this is true of work, then it's also true of heat with a minus sign. And I know all I have to do is talk about heat, reversible heat versus non-reversible heat. And then I just divide them by temperature, and the reversible heat over temperature became entropy. Anyway, that's where this came from. I'm not going to rewrite it. I already did it. So just to remind you that all this comes from a fundamental truth that we know about reversible versus irreversible work. And it's very easy to understand that. Remember those graphs that we did in that homework where you looked at forward and backward work, and reversible work is always the greatest negative. And again, we did it with heat. All right, now, here's where this gets batty. Let's do this at constant, this at constant volume. Okay, let me start out. And remember the equals, the greater equal, that equal is when I'm talking about a reversible process that goes here. Obviously I've left a blank. What should I fill it with? Now, all right, I've got heat. And I've got heated constant volume. I can still stick with DQ, but I'm writing the same thing. That doesn't make sense. What else could I put in its place? Yeah, changing U. Right. There we go. Yeah, that looks like it with the. Yeah, there we go. Okay, now this is where this gets kind of interesting. Let's analyze what this is. Now I'm talking about U, so again, I'm always going to be, from now on, I'm always going to be invoking this path independence. I'm going to do it a hell of a lot. Yeah, doing great on time. So I can build relationships with one path and apply it to others. I can always do that when I'm talking about U's and S's. And so I'm going to do that right now. I'm going to say that I am going to think about a truth of, what am I going to do? How about isothermal reversible? I'm going to create a truth from that and apply it to everything because I can, because I'm dealing with state variables. And that is that if the heat, now this is really important, this is the heat of the system, put a little note in your notebook in case you forget, is equal to the change in U, therefore, the change in the heat of the surroundings, so don't forget I'm not going to write out surroundings, I'm already getting carpal tunnel syndrome. Therefore, the heat of the surroundings, because this is going to give me the entropy of the surroundings, is then what? Remember, heat in is positive, heat out is negative. When I am standing on one side, I see a positive, but if I was on the other side, I'd see a negative, right? Because if I gave you heat, that's positive to you, but it would have been negative to me. Ergo, this is the heat that the system was supplied by the surroundings. Let's say it's positive, then this would be negative. It would be negative or negative.
CBD2.
Be more general, change in U. Minus the change in U. Therefore, now again, this wouldn't have applied to adiabatic, but it doesn't matter. It utterly doesn't matter that this is not true for adiabatic. It's only true for isothermal when we have heat transactions, but it doesn't matter. I'll still apply to adiabatic. Okay, so this is the change in the system, and then this is the change in the surroundings. Oops, sorry. So this is my point. Do you see that? This minus U is the heat of the surroundings. Heat of the surroundings over temperature is the entropy, the change in entropy of the surroundings. Remember, heat's only a change. And that's equal to the change in total. And that must be greater than or equal to 0. There, it's kind of clever, huh? So here's why Clausius was important. Because it can be easily relatively manipulated to becoming a statement of total entropy. Again, it's the second law. I've basically proven the second law. Those laws don't have proofs, they just are, is. And so, I just think that's so cool. You don't hear it anyway. I do think that's very neat. And it also shows, now remember, it says that total entropy of everything. This is the entire universe. Would it help if Neil deGrasse Tyson was giving this lecture right now? Probably would. This is the entropy of the entire universe, because this is inside and outside, and that's everything. And it says the entropy of everything only increases or at best stays the same, generally doesn't stay the same. And so again, this is true of the entire universe, because inside plus outside is everything. And I proved the second law just by looking at some graphs of reversible versus irreversible work. And it gave me a theory about how everything on this entire existence works. So I thought that was kind of neat. All right, but now what I'm going to do is I'm going to manipulate this equation for total entropy and its inequality. It's not actually going to be terribly important. I'm going to manipulate this statement of total entropy further. So that's the point. Okay, now, here I'll erase this because this isn't terribly important. Okay, this is where it gets really kind of neat. If this wasn't neat enough, I think this gets really neat. Let's see, what do I want to do? Multiply by t. I'll spell it out in case you get lost. Okay, I'm starting here. multiplied by T. And, okay, so I got TdS minus the change in U is greater than equal to 0. Now I'm kind of stuck, so I'm going to say at constant S, that goes away, so minus the change in U is greater than equal to 0. I don't like minuses, so I'm going to say the change in U is less than equal to 0. Okay, so what? Here's the point. I started with an equation of total entropy, and I kind of ended with an equation of total entropy. I did some manipulations. I held something constant, but so what? That doesn't really change the nature of the equation. It doesn't become a different equation just because I put a rope around it. A horse is a horse even if you tie it down. God, that's horrible imagery. Anyway, so again, total entropy, multiplied by temperature. So I kind of screwed up the units, but I'm still talking about total entropy. Okay, so that means that if U is negative, if a change in U is negative, tell me what happened to the total entropy. Did it increase or decrease? Now remember, this equation says the total entropy must increase or stay the same. I've done some simple manipulations. This does nothing. This, remember, you've seen why I'm obsessed with does it go up or does it go down. Entropy, does it go up or does it go down? Is it positive or is it, total entropy, is it positive, is it negative? Now, I take a negative number and I multiply it by a positive number, I get a negative number. It doesn't change anything. I get a positive number, I multiply it by a positive number, and I get a right. So this doesn't do anything. It just gives me a mathematically easier thing. All right. Again, total entropy must increase. If delta U is negative, then total entropy increased. Right. And that means that the process was spontaneous. All right. Therefore, change in U. If the change in U of a process is spontaneous, then it's negative. That's wrong, isn't it? So bad. Because I get too excitable. Okay, so now I've shown you that if you can calculate the U of chemicals before and after, and if that change in U is negative, then that's a chemical process that occurs. Now, I warned you this last time. Now, before you were told delta G's got to be negative, right? From high school and freshman, maybe even analytical, I don't know. But now I completely belied that. I said change in U, which you probably haven't even heard of. Okay, you have, but anyway. I've upended that. I've now said, no, forget delta G. And by the way, this is correct. This is correct. Delta G doesn't matter. It does not matter, but why? Why did this guy end up being, so this, I call this the winner. This is the winner. This thing tells me whether something is spontaneous. That's the most important thing I could ever know, because that means it happens. But why is it not delta G? Can you guess?
Delta G is a function of U.
Yes, delta G is a function of U. That doesn't answer the question. It's a good try. All right, here's a hint. Hint. How did I get here? I had to decide, I had to make certain course corrections. I had to make certain stipulations. What were they? Constant entropy was one, and I had another. Constant, right. Constant volume and entropy. Yes, you see, it depended on the stipulations. The stipulations led me to this relationship for total entropy times temperature. Doesn't matter, forget it. Temperature's always positive. So this is total entropy. Total temperature, forget it. But I only got there by making certain stipulations. Now, let me do another one. I said, you know, at constant pressure and entropy, then I'm not even going to prove it because it's impossibly simple. It's the same damn thing. If I hold pressure constant, then I would have had an H as opposed to a U. right? So, I don't see delta G again. Where's delta G? Now, enthalpy you were familiar with. You were taught enthalpy before you were taught delta G. You were taught enthalpy, which is under this, oh, it's cold, oh, I put salt in water, it got cold, oh, I'm burning gasoline in my hands and they're on fire, that's hot. You understood enthalpy just fine. And then you had to learn entropy, which probably wasn't very clear, and then you got delta G. But here I'm saying that delta G doesn't matter, and I am correct. I am correct about this. Delta G is irrelevant to this process. Whatever that process is, a tree falling over, my hands are on fire, whatever. Okay, now here's my point, is that it mattered what was held constant. So, let me just point this out to you, and then we'll break this after turn your homework. I know I want to keep talking, but I know I won't be too late. Okay, so we talked about holding volume constant. How smart is that? All right, we're going to talk about chemical reactions, and I'm going to hold the volume constant. Is that a smart idea? No, you almost never do that. In fact, I don't think you ever did that in your labs. It's way too dangerous. Some people do it, though. They have these, sometimes they're called bombs, actually, like in a bomb calorimetry. It literally is a bomb, all right? It's like a metal baton that you can open up and it's hollow. Close it up, you can put it in an autoclave. And a lot of people do that to make synthetic minerals, which is actually kind of useful for a lot of stuff. But for the most part, we're not going to do this. When you were in organic lab, you did a lot of stuff in an open beaker, constant, right, pressure. Now, even if the chemicals are in, I know that was a little hard to think of, right? You have these chemicals dissolved in this volume of liquid. That's how you did almost everything. And therefore, you might think, well, I don't know, it was in 100 mils. No, it was open beaker, it was constant pressure. Absolutely correct. That's the safe way to do things. And again, the tree grows at constant pressure. You fly your kite at constant pressure. Everything happens at constant pressure. Now, when you were doing organic, you probably put a lot of things in an oil bath, and you kept, what constant? Pressures aren't constant. Things in an oil bath, things in an ice bath. Constant temperature, right. So a lot of your organic reactions, heat bath, ice bath, salty ice bath, whatever, those were done at constant temperature. Constant pressure, constant temperature. Now my point here is if you did things at constant pressure and constant entropy, then delta G was irrelevant. It was delta H that would have told you whether your reaction goes or not, whether you get the high yield that your TA requires and you get an A. All right, so now I told you about the ice bath and the oil bath. All right, now do you remember the time you used the entropy meter? Entropy regulator. It's a meter regulator. It's like the temperature probe, except the entropy regulation part looks like a fish. It wears a top hat. And if you look into it, it looks back at you. It steals your soul. Entropy regulator? Who's seen an entropy regulator? You don't have an entropy regulator. No one has an entropy regulator. They don't exist. You have temperature regulators. Now, before I get back to your homework, last question. If P and T are held constant, guess what letter's there? One of you said 0. G, I don't know. What could it be? G. It gives energy. Okay, homework. Again, I will have your next set 9, 10 o'clock sometime. I'm going to start with Z's. Z's over here. Z's.